you all for coming in this terrible weather. In my talk, I will try to persuade you that about 70% of the universe is made out of so-called dark matter, which is a stuff that has very strange properties. So I will split my talk into 4 parts. In the first 2 parts, I will try to give you some experimental evidence why we believe that's the case, and explain what I mean by these strange properties. Then in the 3rd part, I will tell you a little bit about the history of this idea, how dark energy came into existence, then disappeared, and then appeared again. And in the end, I will tell you about our best guess as to what properties of dark energy should be. So let me jump right in, and let's talk about stars, their lives, death, and what we can learn out of it. If you get outside of Toronto, you are lucky to have a cloudless sky. You could see something like this, a nice vista with lots of stars that looks very peaceful and quiet. But if you look at individual stars, they're anything but peaceful. Right? They're literally balls of fire. It's very high temperature. You see all the violent eruptions going on, maybe, at the rims over here. And what's going on inside these stars is you have temperatures and pressures that are high enough that you can take 4 protons, collide them together in these conditions, and create an atom of helium. When you do this nuclear reaction, there is energy that's being released, and this energy is supporting stars from collapsing. Normally, what you would expect is stars are very heavy, so they would collapse under their own gravity. But because of this injection of energy, there is a very fine balance between pressure and gravity. However, stars have only a limited amount of fuel. Right? They are not like us. We can take a lunch break, go to canteen, and refuel ourselves. The stars cannot do it, and once they run out of fuel, they die. What exactly happens, how exactly they die, depends on lots of properties, but in some cases, this is what happens. You have a star, and then it explodes. We call it, star goes supernova. And while there is some matter that's being ejected, maybe you can see it over here, for us what will be important, there is a lot of light that's being shown into the universe. Right? The supernova explosion is so bright that for a brief period of time, supernova can be brighter than the rest of the galaxy combined. So you have billions and billions of stars, and together they are not able to produce as much light as this one single explosion. So these explosions are so bright that you can actually see them with your naked eye during daytime. And so over history we have lots of records in Indian, Chinese, Middle Eastern, European literature about people seeing, oh, look, there is a new star appearing in the sky. And it was always such a big deal that, for example, back in 1606, Johannes Kepler wrote a whole book about a new star appearing in the sky. Fortunately, these days we don't have to rely on human observers to search for supernovas. This is an image of a so-called Vera Rubin observatory, named after famous astronomer Vera Rubin. And part of this Vera Rubin observatory is the best digital camera we have at our disposal these days. It's 3.2 gigapixel camera. Oh, can you hear me the whole time? Anybody at the back can wave that they're okay? Thank you. Apologies. Right. And it turns out that if you want to see this huge photo taken by this camera, in the native resolution, you need 400 of ultra-high definition TVs to actually see it. So it's a huge picture. And we are taking picture every 15 seconds. But it's an enormous amount of data that we are collecting about the universe. And this is what we are searching for. So imagine yesterday, February 5th, you take an image of a galaxy. Of course, you won't see the yellow light, the yellow arrow. It's just telling you where to look. And today, you are observing again, you take a different picture, and you appear there is a white blob appearing, and it will stay there for a week, 2 or 3, and then eventually, something like a month later, it will disappear, and you will go back to what you saw before. And this is evidence of a star exploding in a faraway galaxy, emitting this light that we can observe today, and after some time, it vanishes forever. Now, even astronomers sometimes ask questions like, what is it good for? What do we learn? So let me start by explaining a basic concept in astronomy. If you have an object, then if the object is nearby, it's bright. And then if you move it far away, it's faint. So if you imagine you have a standard light bulb, by measuring how bright it is, you can determine how far the light bulb is. Right? It's seen here in these street lights. This guy is pretty close, so it appears to be bright. And these guys are far, so they are faint. Everybody with me? Okay. Now, let me assume, for the purposes of this talk, that all supernovas are the same. Okay? They are the standard light bulb. So if we measure how bright they are, we are able to determine how far away they explode. Of course, this is not perfectly true, and there are armies of people studying to what extent this is actually true. There are various classes of supernovas, and you have to do some tricks, but for the purposes of this talk, let's assume this is true. Okay. So, your experiment will go like this. You're taking pictures of the sky, and eventually at one point, the supernova appears. So you take note of its location, when it happened, and other properties, and you store it into your computer. Sometime later, you get a different supernova. Now this one is brighter. So oops, sorry, that's not what I wanted. This one is brighter, so I draw a bigger circle. Now everybody knows what it means that supernova is brighter, right?
Closer.
Excellent, thank you. So this one is closer. So, oops, wrong direction. So we store it, then we have one with fainter, it means it's farther away, and we store it again. And after some time, we have a large collection of them. Astronomer would say we have a catalog of supernovas. Some of them are nearby, some of them far away, but we have a nice sample. Now, let's come to the second important point, and that is that supernovas actually have colors. This is a very simplified cartoon, but I'm trying to... Very loud. I'm trying to illustrate one basic thing. So can anyone tell me what is the basic thing?
Composition.
Composition?
Right.
No, I'm trying to connect the colors with...
Redshift.
Okay, it's related to redshift, but what I'm trying to say is the big guys are blue, and the small guys are red. As simple as that. Is there a question at the back?
I just wanted to put, from now I'm going to say redshift. You're trying to illustrate redshift in this.
That's correct. I'm trying to illustrate redshift. For those of you who are not here for the first time, yes, this is indeed redshift. But the basic idea is objects, supernovas that are nearby appear to be blue, and guys that are far away appear to be red. So how astronomers plot this information is they would make a two-dimensional graph with color on the horizontal axis, going from blue to red, and the distance from near going to far from the bottom to the top. They would take your sample of supernovas, and you would find out they actually follow on this nice straight relationship. Now, let me unwrap one simplification I made. I was hoping you would see the red-blue relationship, but in reality, supernovas, of course, have all sorts of colors. So you would go from blue, through green, through yellow, to red. Okay. Now you can start wondering, so maybe this is telling us something about how supernovas are behaving, but it turns out that galaxies are doing exactly the same thing, and other objects too. So things that are nearby in the universe appear to be bluer than things that are far away. So it looks like we are finding something that's universal, something that's telling us something about the universe itself. I made a video where I'm trying to show what our current understanding is what's going on. Currently we believe that the universe is expanding. And as the universe is expanding, the distances between individual galaxies are increasing. So you will see the galaxies moving away from each other. And there's a second thing which you will see. There will be a supernova exploding at the galaxy here at the bottom, and you will see light propagating through the universe as it's moving towards us. We are sitting in this galaxy over here. Right? So let me just play the video if I manage. Okay, so everything is expanding with the universe, and there's this light, and the light is slowly making its way through the universe, and as it's making its way through the universe, it's changing color from blue at the beginning, through green, now it's yellow, orange, and finally red when it hits us in the galaxy over there. Okay? So this is our current understanding of what we are observing in the supernova data. Let me try to explain in a little more detail why we believe this is the case. And I'm sure many of you have seen this image before. If you take a white ray of light, for example sunlight, and you shine it onto a prism, it decomposes into various colors, so you get a nice spectrum in the end. And the reason why this happens is because light is a wave phenomenon, and color of light is related to the wavelength of this wave. And waves that are having long wavelengths appear red to our eyes, and light that has short wavelength is blue. Okay, so long wavelength red, short wavelength blue. And I apologize to half of the audience that's proficient in redshifts. So this is what happens. As the universe is expanding, you take this wavelength, and it's stretching with the expansion of the universe. And as you increase the wavelength, the color is changing from blue originally, oops, sorry, make it clear again. From blue, sorry, it's not my computer, to green, and again orange and red. Okay? So the basic idea is the longer the light has been traveling through the universe, the redder it appears. If you have a supernova that's nearby, the light traveled only for a short period of time, so it didn't have time to redshift all the way to red. If you have supernova that's far away, you have a lot of time to change color, and so you see things that are redder. I apologize, this is the only equation that will be present in this talk. If you sit down, write down what general theory of relativity predicts, you will find out that there is one-to-one relationship between how quickly the universe is expanding, how quickly these galaxies are moving away from each other, and how dense the universe is. For those of you who are trying to remember what density is, this is a cartoon. If you have a given volume, illustrated by the white box in here, then dense universe is a universe where there is a lot of stuff. Galaxies matter, dots in this case. And then you can have universe that is not so dense. There are much smaller number of galaxies. And theory of relativity is telling you that dense universe is expanding quickly, and universe that is not so dense is expanding slowly. Okay? And the punchline is, with this understanding, you're able to perfectly understand this behavior between color and distance of supernovas. So that's really nice. However, while we were doing our calculations, experimentalists work on, and they get better technology. They're able to see farther in the universe, they're able to see fainter objects. And so they start taking new data. Right? This is what we had. And then if you take new data, new points will appear at the top, you can see it, and eventually you start seeing a divergence. Something interesting is going on there. And to illustrate that you've actually learned quite a bit already, let me show you a plot from an actual scientific paper. This is from 1998. And let me help you unwrap what's going on this plot. Right? So let's first get rid of the scientific notation on the axis. This is what you know, right? Things on the left are blue, things on the right are red, things at the bottom are near, things at the top are far. All of these data points represent measurements of individual supernova. And as I told you, we have some understanding for how the universe should be behaving based on general relativity. And there's a dashed line here, which you can barely see, but I tried to make it clearer in red. So this is their expectation. And the big punchline is that the points, the supernova measurements, are actually above the dotted line. So really there is something interesting going on in there. And it was such a big deal that back in 2011, people who made this measurement got the Nobel Prize for it. And why they got a Nobel Prize for it? Well, let's start thinking about what gravity is. So from the first science experiments we made in our parents' bedroom, we know what gravity is doing. If I take the laser pointer and I throw it up to the ceiling, two things happen. Well, organizers get really stressed out. And then eventually it comes back, because it's attracted back by the Earth's gravity. Now, galaxies are expected to do exactly the same. So, at the moment they are expanding with the expansion of the universe, but eventually gravity will start pulling them all together. And so, in some scenarios, even you can see this trend reversing and galaxies starting converging back together. Right? So gravity is expected to bring things together. And so what you would expect is that the velocity with which galaxies are moving away is decreasing with time. However, if you express what we see in supernova data in terms of the galactic velocity, this is what we see. Originally, the galaxies are behaving well, and their velocity is decreasing, but eventually they decide they don't want to do it anymore, and they start running away faster and faster. Right? So that's why we call about so-called accelerated expansion of the universe. And to make it even more clear, this is a real-world analogy. Imagine you're playing basketball, and originally the basketball is doing what it should be doing, and then they decide it will just okay, so that's not how gravity is supposed to work at all. So something's wrong. Whenever someone is trying to sell you an interesting experimental result, this is the first thing that should be on your mind. If anyone in the audience remembers the time when we had neutrinos that were moving faster than light, this is one of those cases. I made this huge deal about how supernovas are all the same. Well, they are not the same, right? So there could be something wrong about it. But in general, whenever you have a new discovery, you are trying to make an independent measurement with a different method. And so in the second part of this talk, I will tell you about an independent method. And it turns out it comes to similar conclusions. So it might be that our understanding of how gravity is working is wrong. There has been many proposals, as far as I can tell. General relativity is still the best one, but I encourage anyone to try. There is a long list. I don't know all the possibilities, but let me tell you about what we currently believe is the best solution. And the best solution is that there is extra stuff in the universe. And for lack of a better name, we call it dark energy. And there are various ways how you can include dark energy into our universe. The simplest way is if you go back to this equation that's telling the universe how it should be expanding, is you just add a constant to one of the sides of the universe, of the equation, sorry. So you have a density of the universe, you add a constant, and that's telling the universe how it should be expanded. And it turns out that this one constant is able to explain all the cosmological data we have. The supernova data and other data I'm going to talk about later. So we call this constant cosmological constant, and sometimes you see the Greek letter lambda written to denote it. To give you an idea of how small this number is, it's 10 to negative 29 grams per cubic centimeter. And if you're as scared as small numbers as I am, imagine if you take the volume of the Earth, right, this huge volume, then the extra mass inside this volume is equal to the mass of the feather. It's really, really tiny. But because it's the same everywhere in the universe, and it's the same at all times, it can have a fundamental impact on how our universe is actually behaving. And of course, the fundamental property of this matter is providing anti-gravity. The regular matter is trying to pull everything together, and this dark energy is somehow trying to tear the universe apart. If you look at how much dark energy there is in the universe, it turns out it's about 70% of the energy today is this dark energy, and only 30% is matter that's having the regular gravity as we know it, where the basketball is going down. What is interesting is this graph is actually changing in time. As the universe is expanding, there is less and less matter. So if you go back enough in the universe, there was almost no dark energy, and most of it was matter. And that's why you saw in the plot where the galaxies were moving together initially. But at some point, the matter got so diluted that dark energy prevailed, and now everything is expanded. There is a second twist. If you look at the matter that's behaving normally under gravity, and you calculate how much of it is formed by electrons, protons, and stuff you and me are made of, it turns out it's only a small fraction of this matter that's present in the universe. And so we call the rest of the matter, we don't know, dark energy. And this is the topic that Vera Rubin makes some of her most famous contributions. So dark energy is stuff we don't know, that's behaving really under gravity. And dark matter is stuff we don't know, that's behaving normally under gravity. And together they are 95% of the universe. Okay, so that's end of my first part. Let's talk about the second piece of evidence. How am I doing on time? Okay, we're doing good on time. Second piece of evidence why we believe there's something like dark energy. Alright, so imagine you have a lot of space in your garden and you don't know what to do with it. So one of the things you can do is you can build yourself a radio telescope, something like this. Once you have a radio telescope, you look into the skies and you find there's an interesting signal. It turns out that its intensity is the same in all directions, and it has a temperature of roughly 3 Kelvin. So in normal units, it's negative 270 degrees Celsius, or negative 455 degrees Fahrenheit for those from the US. So it's quite a bit colder than Toronto winters. And our current understanding is that it's light, some radio light that's coming from the early universe. And if you take our image where the universe is expanding, we can play the movie backwards. And as you go backwards in time, the universe is denser and denser and warmer and warmer. And so those conditions that today we can only find inside stars, they used to be everywhere. But as the universe is expanding and cooling, eventually you cannot sustain these nuclear reactions any longer. And at some point you get to the moment where light can just travel through the universe freely. And some of this light has been detected by your radio telescope in your garden. Okay. You've been traveling through the universe for 13.5 billion years until you caught it. Good job. We call this light cosmic microwave background, or sometimes Rayleigh radiation. And for those of you who remember that TVs used to look like this, about 1% of this noise, which you detected, was formed by this Rayleigh radiation from early stages of the universe. Now imagine you have a neighbor who starts building a radio telescope in their background, and you want to do better. Well, you can spend something like $1 billion and build yourself a satellite, something like the Planck satellite here, with, by the way, significant Canadian contribution. And you can map the cosmic microwave background into exquisite detail. It turns out that it's actually not the same intensity in all directions. There are tiny, tiny fluctuations at the 0.01% level. So in some directions, this light is slightly warmer, and in other directions, this light is slightly colder than the average. And this just relates to the fact that some places in the universe are denser than others. So what is actually shown here is a map of the sky. So it's the same as if you have a map of the Earth. You take a sphere, you plot it into the plane. Here you take the map of the sky with temperatures. Red means the temperature in the given direction is warmer. Blue means the temperature in the given direction is colder. And you just plot it into a plane. So this is temperature of the universe in cosmic microwave background. Why it's such a big deal is because there is enormous amount of information about what the universe is composed of and how it behaves. Now I have 3 slides that are kind of tricky, so I'm worried like 75% of the audience will not get it, but don't be scared, you're not alone, and I'll have a summary slide of what I'm trying to say, okay? So 3 slides, let's be a bit more technical. Now we'll start by analogy. If you take number 912,532 in the base of 10, you can think of it as 9 times 100,000 and so on, right? Very simple. And it turns out that with this 2-dimensional map, you can do something similar. There is a basis set of maps that looks like this, but there's plenty of them. And you can expand this map into these fundamental maps, so to say, so you do a linear expansion for those of you who are more familiar with math, and there are some coefficients in front. Okay, so now you have this expansion, and then you try to compress information from these coefficients into a one-dimensional plot, where the coefficients are on the vertical axis, and the size of the blobs in these maps are on the horizontal axis. So we have this map, which has fairly big blobs, and there's 3, so we put it here, to this part of the graph. And then we have a map with smaller blobs, so we put it to the right, and there is 1, so there is a smaller value on the vertical axis. Okay, if you lost track of what's going on, now please start paying attention again. If you give me a map, there's a well-defined process, there is a computer program I can feed it into, and it spits something like this. Okay, some one-dimensional information that's encoding statistical information about a hot and cold spots in this map. And if physics friends are trying to impress you, they call it power spectrum. But it's really just some transformation of 2D information into 1D information. And the reason why this is so fundamental is because if we take our understanding of gravity, general relativity, and we take the lab measurements of how light is interacting with matter and matter with itself, and on top of that we add that the universe is 70% dark energy, 25% dark matter, and 5% the rest, we can make a prediction for how this curve should look like. And it turns out that the data shown here in black from the Planck satellite and the prediction shown here in blue match very, very well. Now the punchline is that you can make the same prediction assuming there is no dark energy. Then you get something like this. Ooh. That doesn't look very well. So unless you have dark energy in your universe, you're not able to explain the cosmic microwave background data. And so that's the second piece of evidence why something like dark energy should be in there, and it's using different experimental technique, different data sets. So it's kind of strong evidence that something like dark energy actually exists. And this is not all. We have measured positions of millions of galaxies. Again, we can do some statistical tricks, and we come to the same conclusion. There should be something like dark energy in the universe. Now, I'm painting a very rosy picture about how we understand everything. There's an elephant in the room. And it's such a big elephant that there was a whole AstroTours talk back in October. So if anyone is interested in a topic, I encourage you to go online and search for it. And the problem is that we are currently uncertain how quickly the universe is expanding. So we have several measurements, and some of them tell us that the universe is expanding more like a cheetah, and others are telling us that the universe is expanding more like a snake. Now, your mind should go back to our bullet point list, right? Maybe someone messed up. Maybe the supernovas are wrong. But it could be that there's actually some interesting physics that this discrepancy is pointing to. So it's definitely interesting to keep this in mind and see what's going on in the future. Okay, so that's the evidence I have for you. Now let's talk a little bit about how dark energy and its idea originated and propagated in time. Back in the 1970s, of course, this guy came with the first idea that something like dark energy should be in there. And at the time, he already knew how gravity should be working. He had this general theory of relativity. And he was trying to apply it to everything, the whole universe. And it turns out he had an agenda. He wanted a universe that's unchanging. He wanted the universe as it looks today to be the same as the universe, how it looked in the past, and the universe as it looked in the future, how it's going to look in the future. And there's a problem. You all know now that the gravity is trying to change the universe, it's trying to compress it. Well, so Albert Einstein figured out that maybe if he adds something like cosmological constant into the theory, he can have just enough anti-gravity to balance the gravity of the normal matter. And so, if he tweaks things and adds cosmological constant, he can have a universe that doesn't change in time. And that's what he wanted. It turns out that's not true, and I don't want to talk about the technical details why it's not true, but even with cosmological constant, you cannot have a universe that's just unchanging. So 10 years later, we got first of these graphs that told us that the universe actually is expanding. And And that led Einstein to say that coming up with cosmological constant was actually his biggest blunder. But now we know that cosmological constant actually exists, so maybe Einstein saying cosmological constant was his biggest blunder, was his actual biggest blunder. So then for 50 years, we didn't need cosmological constant at all. It was not a topic at cocktail parties. We thought we understood the universe pretty well. 50 years. And then around late 80s, early 90s, cracks started to appear in our understanding of the theory. Maybe not so bad cracks, but it wasn't good. And one of the famous examples of what went wrong is we got measurements of the ages of the oldest stars. And it turned out that these stars were older than the universe itself. Not good. People started thinking about, okay, so how can we solve this? And it turned out that if you add something like cosmological constant into the universe becomes older, so it can stretch its age to where you need it to have. And then, of course, 1998 happened, and we had this wonderful measurement that told us that cosmological constant actually seems to be the way out. And since then, we've taken a lot of other cosmological data, and it all matches with this one problem I mentioned that's pretty recent, it's still unsolved, and so now we think we understood the universe pretty well. And the phrasing is not accidental. Alright, so in the last few minutes, let's think about what it might be. What is this dark energy? And let me remind you that the cosmological constant corresponds to density that's really, really small. And that's kind of a problem, because if cosmological constant was 0, there would be an easy way out. You would just come with some principle that forbids cosmological constant from happening. These things are easy in theoretical physics. But now we know it's actually in there, and we have to explain why it's so small. And that's tricky. So the honest answer is we have no clue. So if you have a good teacher and you're at an oral exam and you say, I have no clue, well, what do they say? Well, at least guess something. So let's guess. There are people doing particle physics, and they have these wonderful machines, particle colliders, such as this, Large Hadron Collider in CERN, in Switzerland and France. And what they do, they take elementary particles, they accelerate them to very, very high energies, and they smash them together. And after they smash them together, they look at the debris and try to understand what happened. So it's something like you take two cars, you smash them together, and from the parts that are flying around you are trying to understand how car is working. That's what they're doing. But it looks like they sort of understand what they're doing. So they have some mathematical techniques that are able to predict what's going to happen. And so we can use these techniques to make a prediction for how big the cosmological constant should be. And this is just like a really simple cartoon, no one should take it too seriously. But part of their calculations is concept of virtual particles. So because of quantum mechanics and principle of uncertainty, you can have two particles come up out of nothing, exist for a brief period of time, and then recombine again. Right? And there is some energy related to these pairs of particles created out of nothing. And they contribute to this vacuum energy that we believe is responsible for this expansion of the universe. And so if you are a first-year graduate student, you can use this machinery to make a calculation. And it turns out that your result is 122 orders of magnitude off. So the ratio is this. There's 1 and 122 zeros. And I assume everybody would agree that's like a failed grade. If you are higher up in graduate school, you can make a better calculation. Because, first year grad school, they don't know anything. And you improve the calculation to 58 orders of magnitude wrong. So you get rid of 1.5 lines of zeros, but there are still plenty zeros left. So let's still fail. Maybe fail plus for effort. But it brings me back to the same conclusion. We really have no clue why cosmological constant should have the value it has. And so this is my summary slide. I hope I persuaded you. We have some good evidence. There should be something like dark energy in the universe. should be trying to tear the universe apart, but we really have no idea why it's having the properties it has. So if you guys like puzzles, this is a really good puzzle. It's a good prize in the end if you solve it. Okay, good luck.
So we'll let Pavel have like a short break, turn to the person sitting next to you, ask them your question, and then we'll come back together and then you can ask Pavel your questions. All right?
Gravity is caused by things of massive dark matter, by the virtue of mass. Some sort of matter also has mass and therefore has gravity that pulls things together. So what kind of properties, based on what we know of, would cause things to have that anti-gravity effect? Is it just the background from the quantum effects, or is it some sort of, or if it's a particle, what kind of properties would it need to have in order to yield that effect of anti-gravity?
Well, so naive.
Pavel, could you repeat the question?
Oh, sorry, thank you. So the question is, if I understand it correctly, is what kind of properties would the dark energy have to have in order to make the universe expand, right?
That's just.
Okay, so we sort of thought we know what needs to happen, right? We have some understanding of how the vacuum should be behaving under these vacuum fluctuation, and it turns out it's not correct for whatever reason. And so then we don't know. You ask what the properties would be of the particles. Well, the problem with the particles, right, is that normally you have a finite number of particles, and as the universe is expanding, their density is decreasing, right? Their energy is being diluted. And that's not how the dark energy seems to be behaving. It seems to be constant in time. And so it's hard to think of ways how something related to protons or particles like that would be having this weird property. At the front?
It seems to me that the dark energy is based on the assumption that the laws of gravity that we figured out in our solar system applies to the whole universe, right? But why do we think so? We may have other laws for the rest of the universe, or all the other pieces of the universe. Like whether it's Newtonian or Einstein, that's all was based on our observations in the solar system, basically. So it seems to me that it's just a fudge factor to actually apply our laws and get it to work for the whole universe.
Okay, so the question is that our understanding of gravity is based on the measurements we've made in the solar system. And maybe we are just trying to extrapolate to too far distances. Is that the question? So that's correct. And it might be the case, and there are definitely people studying these possibilities, that maybe the general relativity is not the correct theory of gravity. And
just a special case for our solar system.
yes. So there are people working day and night on this, and as far as I can tell, cosmological constant is like the most elegant solution, so to say, if you want to apply some sort of Occam razor, right? Because it turns out that general relativity is very robust. If you try to change it in any ways, you run into all sorts of unexpected issues. For example, there are theories of gravity where you have gravitons, those are particles that are exchanging, those are particles that are responsible for the gravitational force. Something like photons for lights. You have the same thing for gravity. And you can think that maybe these particles, they have some mass. And so you work out how the universe would look like if gravitons have mass, and it turns out it would just evaporate. It would be very unstable. And so people are probing these directions, but so far no one seems to be successful.
Okay.
Go ahead.
goes into nothing with no net effect on its surroundings, how can it, affect the expansion of the universe?
So essentially, so the question is, if we have these particles that appear out of nothing and then disappear again, how can they affect the expansion of the universe, right? That's the question? Good. So it turns out that the quantity which you are trying to calculate is the energy density of the empty space. And so the way you do it in particle theory is you start drawing these Feynman diagrams, and you calculate what is the energy density corresponding to this set of Feynman diagrams that correspond to empty space. Right? Normally you have particles flying in and particles flying out. That's what the particle people study in colliders. But you get the same thing for the vacuum when there are no particles flying in and no particles flying out. And if you do this calculation, you get something that's clearly wrong. So we are doing something incorrectly. It's just no one is able to figure out what exactly we are doing incorrectly. And as I said, it fails. Okay, any other questions? Over there?
Does dark energy share any similarities with regular non-dark energy? Any properties in common at all? Or are they completely different?
Okay, so the question is, if dark energy shares any properties with the matter we know? And the answer is, we have no clue what dark energy is. So we don't really know. We just know it seems to expand the universe in a weird way. It could be that the gravity is wrong. It could be there is no dark energy. Sorry.
We don't know, you say you don't know if it exists, but you seem to see an effect. The thing is, can you measure, the force or the amount of energy that there is, like by calculating that this thing is moving from point A to point B in a certain amount of time?
Okay, so the question is, if I understand it, that we are able to measure how things are moving in the universe. And so maybe from these motions, you would be able to figure out what is the gravitational law, so to say.
Yeah.
And the problem is that most of the matter is dark. We don't see it.
But you can see that these galaxies are moving away from each other. Is there no way of calculating or estimating how much energy is actually pushing these things away at that given velocity?
So the follow-up question is there no way how to calculate what is the energy corresponding to this expansion of the galaxy?
Yeah.
Maybe. We can think about it later. But it sounds like it will take a while. Sorry. Over there.
So we've got data coming from supernova observations and data coming from CMB observations. So what do you need to do the next step in order to produce some observational uncertainties to figure out the expansion? What do you think is the next observational step?
So the question is, we have the supernova data, we have the CMB data. What is the next observational step? And so it depends on what sort of question you are trying to answer. So for the expansion, depends on what range of distances you are interested in. In the ranges where we have supernovas, supernovas are the best measurement. If you want to go farther away, there are not that many supernovas. And so people are thinking about using 21 centimeter measurements. There is hydrogen in the universe, and so there's CMB light hitting it, and there is some signal which we can measure. And that gets you to higher redshifts, larger distances. If you're interested in this, how quickly is the universe expanding, a lot of the interest is in gravitational wave measurements. I'm not sure if you noticed, but if you measure a gravitational wave event, and at the same time you're able to measure the light from the galaxy, it gives you a data point about how quickly the universe is expanding, because you know the distance and you know the redshift, you know the color. And so you have an extra plot in this diagram, which we had before. Sorry, one of these. So you can add a gravitational wave event there. And that's a different object. So we expect it has different errors than supernovas. And that would be a nice cross-check. Oh, sorry, over there.
We talk about the large things
We talk about, sorry, what?
so we are talking about galaxies and all these bigger macro things. Have we figured out whether there is any effect on dark energy or dark matter at the lowest level, like subatomic level?
So the question is that we know about dark energy from these large microscopic observations, and is there any evidence from smaller scales like tabletop experiments?
More than tabletonic at the subatomic level, like what do you call it, quantum mechanics level.
Quantum mechanics level.
The reason is because we still haven't figured out exactly the difference between matter and energy. We haven't resolved it completely.
Right, so this is the problem, right? You're talking about densities that are so small that on these scales, everything else is much more dense than dark energy. So dark energy is just a tiny perturbation on top of your bottle, for example.
Even at quantum gravity level? Quantum
Oh,
mechanics
quantum
level?
gravity.
Quantum mechanics level?
I don't know about quantum gravity. Quantum mechanics seems to work just fine for the people in the labs. Right, so this is really the problem. It's a small effect and you have to go to really large scales, such that overdensities, such as solar system, just average out. They are not significant. You don't have to care about it. Okay, so there's a question at the...
We'll take these two.
Okay, so the last two question, at the back first and then...
Yeah, so if the universe is expanding, is there any evidence that will be more like a dark energy or matter in the universe? Like the ratio of 7% of Terry will increase or change?
Right, so the question is about the ratio of energies. I said that today we have 70% in dark energy and 30% in dark matter. And as the universe is expanding, dark energy, as we currently understand it, has still the same density, but the density of matter is diluted. Right? You have the same number of galaxies in a bigger area of space because the universe has expanded. And so the red slice will go smaller and smaller until eventually it will be insignificant. And there was a question over there?
Sorry, I'll preface this, this probably shouldn't be the last question, Mike, because it may be a very stupid question.
There are no stupid questions.
Going back to your list of things where you could have statistically or just from people guessing it wrong, experimental level.
Right.
Is there any evidence that we found that shows that the universe in parts is not expanding, or is expanding to a lesser degree? Or is it constant expansion that we can see?
So the question is whether the universe is expanding to the same degree everywhere. Did I get it?
Or if we found evidence that it isn't following what we think it should with expansion. Like there's a part where it is not expanding or it's contracting.
Oh, is there like a part of the universe that's not expanding or it's contracting? So, what I was talking about is the universe if you average it over large scales. Right? And it looks like, or at least at the moment I'm not aware of any good evidence, that if you look at, for example, well, I don't want to say the numbers, but if you average over a large number of scales, it looks like everywhere in the universe is the same. However, as you go to smaller scales, you start running into issues, right? For example, you're living in one of the densest places in the universe. Right? So eventually at some scale, I forgot how many light years it is, but you start worrying about galaxies and stuff around you that's more important than things like dark energy. And that's again this density issue, right? Earth is very dense, and so we don't really care about dark energy. But if you average over many, many galaxies, the average density is so small that dark energy plays a role. Does it sort of make sense?
Yes.
Thank you. Okay, thank you all.